Hello, my dear friends. I am A.D. Chandrasekharan. Today I am going to give a lecture on the topic singular points. You see, we have already seen that the function f of z is analytic at a point z equal to a. It means that f of z, it has the derivative at that point and also its neighborhood. Now, this is the contradiction to that. Suppose the given function f of z is not analytic at a point a, then we say that that point is singular point. Once again, I repeat this. Suppose the given analytic function f of z is fails at a point z equal to a, then we named that point z equal to a is a singular point, is often called as singularity of the given function f of z. Okay. Now let us see some examples. Example number 1. Consider the function f of z is equal to 1 by z. Now find its derivative. F dash of z is nothing but minus 1 by z squared. Now this is exist except z equal to 0. Why? When z equal to 0, this becomes undefined. Okay, so thus the function is analytic except at z equal to 0. So z equal to 0 is a singular point of 1 by z. Correct? Second example, f of z is equal to 1 by z minus 2. Suppose if I substitute z equal to 2 in this f of z, the denominator becomes 0. So 1 by 0 becomes infinity. So that means that the function is ceases to be analytic at the point z equal to 2. It fails at the point z equal to 2. The function is fails the analyticity at the point z equal to 2. So z equal to 2 is a singular point. Let's see the third one. It's a trigonometric type example of a function in terms of sin z by z cos z. So what are the singular points of this? It's nothing but find the denominator equal to 0. The roots of the denominator equal to 0. So that means that either z equal to 0 or cos z equal to 0. That means z equal to plus or minus pi by 2 plus or minus 3 pi by 2 etc etc. So these are the singular points of the given f of z. So the singular points, we have already come across this idea when we dealt the Cauchy integral formula. Remember, in the Cauchy integral formula, the denominator is z minus a. So that is the point which fails the analyticity of the given f of z. So this is the simple examples of singular points. Now there are some different types of singularities. These are some more examples for you. Let us see the fourth one, z by z squared plus 1. So let us equate the denominator equal to 0. We get z squared equal to minus 1. So z equal to plus or minus I are the singular points. Fifth one is 1 by sin z. So sin z equal to 0. So z equal to n pi. N is a positive integer. So 0, pi, 2 pi, 3 pi, 4 pi, etc. etc. So it will generate more than one singular points. Yeah. And sixth one, there are two singular points, that is 1 and minus 2. But 1 is repeated 2 times. So it has some specific name. Let us see in the next title what is the name of this power. Okay, because it is one is repeated twice. So what is the name of that one? It is called order. It is called the order, right? Yeah, let us see the types of singularities, types of singular points. The very important type is isolated. So what is the meaning of isolated? Means single. There is one and only one singular point, then it is the isolated singularity. So this is the definition, says that a point z equal to a is called an isolated singularity of f of z if f of z is not analytic at that point, then the neighborhood of z equal to a should not contains any other singular point. So if I draw a neighborhood of that this point z equal to a, what's the neighborhood? Looks like a circle whose center is the origin, and the point, the center is the point a, and the radius is the very smallest value. Looks like a circular disk. So when I draw the neighborhood of z equal to a, and in that circular disk, in that neighborhood, no other points are singular points of f of z. That means that this is the one and only singular point. Got it? Isolated means one and only. That's it. Very simple. And let us see some examples. The first one, let us consider the function 1 by z minus 1 whole square. So z equal to 1 is a singular point and there is no other singular points. Neighborhood of this one. So I once again repeat this, neighborhood means very small circle. You assume that the radius is very negligibly small. Okay. So z is the only singular point. So it's called isolated. Hmm? See the second example. If f of z is equal to z plus 1 by z into z squared plus 1, it has three isolated singularities. When we solve the denominator, we get 0, another one is plus or minus I. Clear? Understand? Plus or minus I. So there are 3 points. It is nothing but the depends upon the degree of the denominator. What is the degree of the denominator here? Z into z squared, so power 3. So there are 3 singular points, right? And 0 is 1, I is 1, another one is minus I. So these are the one and only singular points, so they are called the isolated. There is no other singular points in the neighborhood of z equal to 0. Okay, in this third example, sine of 1 by z. Yeah, when I substitute z equal to 0, we get infinity, so it becomes undefined. So z equal to 0 is an isolated singularity. Correct? See the fourth example, 1 by sine of z. So see the difference between third and fourth example. Third one is sine of 1 by z, but fourth one is 1 by sine z. So the denominator equal to 0 means sine z equal to 0. When we get sine 0, that is sine z equal to 0, 0, pi, 2 pi, 3 pi, plus or minus pi, plus or minus 2 pi. So these are the many, some infinite number of singular points, because I told you that when I draw a neighborhood of z equal to 0, then pi, what's the pi value? 3.14. So somewhere it is, right? Because the radius of the neighborhood is very small. Pi not 1. Like 2 pi and 3 pi, 4 pi. So these are all the isolated singularities of the 1 by sin z function. Now I have some more types of singularities, but hereafter we can classify the isolated singularity into 3 types. Isolated singularity into 3 types. So the minimum default is isolated singularity. This is the one and only singular point. Now the first type is removable singularity. Removable. It will remove certain terms of f of z. That is actual the meaning of this one. Let us see the example. There is a see the definition of removable singularity. A point z equal to a is called removable singularity of f of z. Removable singularity of f of z. Then first of all, the point is an isolated singular point, and the limit value is exist. Limit z equal to a, f of z is exist. So this is the one way of definition. In other words, if I expand the f of z as the Lorentz series expansion at the point z equal to a, then in the principal part, do you remember what is the principal part means? Negative powers of z minus a. Remember the Lorentz series expansion, the previous topic? The negative powers of z minus a. Why it is called negative powers? Because we have considered the singular points only from the denominator function, isn't it? So in the principal part of the Lorentz series expansion of f of z at the point z equal to a, it has no term. So there is no principal part in the Lorentz series expansion. It means that generally the Lorentz series consists of two parts. One is the regular part, another one is the principal part. Now here this point z equal to a is an isolated singularity, and when we expand as a Lorentz series expansion, it is completely removes the principal part. So that's why this point is called removable singularity. Got it? Now the examples. The first example, sin z by z. So denominator equal to 0, z equal to 0 is the only singular point, so isolated singular point, and the limit value is also exists. What is it? Limit theta tends to 0, sin theta by theta is 1. Otherwise, here z tends to 0, sin z by z is 1. And this is called the removable singularity. So this is the one way of definition. What is another way? If I expand this f of z into the Lorentz series, see that? What is sin z? As we already know that sin z is z minus z cube by 3 factorial plus z power 5 by 5 factorial minus etc. Now what is sin z by z? So sin z is this much divided by z. So if I pick z from the numerator and cancel this z, then the rest is this one. So let us see this. There is no principal part, only the positive powers of z, that is the regular part. So there is no principal part, there is no negative powers of z. So, and also when I substitute limit z tends to 0, we get 1, isn't it? By z 0, 0, etc. So in this Lorentz series expansion, the principal part has no terms. There is no principal part. So that's why this point z equal to 0 is known as the removable singularity of f of z. Got it? The second one, f of z is equal to z minus sin z by z cube. Once again, z equal to 0 is the one and only singular point, right? Let us expand this with the help of the sin z expansion. We get z minus z cube by 3 factorial plus z power 5 by 5 factorial minus etc. After minus multiplying to the term, then cancel the z, divide by z cube. So z cube by 3 factorial, here also z cube. When I divide by z cube and term wise, we get 1 by 3 factorial minus z squared by 5 factorial. See that? Once again, there is no negative powers of z. That means that there is no principal part. And also when I applying the limit as z tends to 0, from this term is 0, hereafter everything is 0 except the first constant term 1 by 3 factorial 1 by 6. So limit is exist, as well as there is no principal part at that point is equal to 0. So that's why this is known as the removable singularity. Clear? Third example, f of z is equal to z squared minus a squared by z minus a. So if I equate the denominator, we get z equal to a is the one and only singular point, it's an isolated point. Then let us apply the limit z tends to a, z squared minus a squared can be written as z plus a into z minus a. After cancelling z minus a, we get z plus a. Substitute a here, we get 2a. So limit is exists. So it is the removable singularity. Clear? Right? So the aliter z squared minus a squared. So after taking the minus a from the denominator, we get this one 1 minus z minus a. Let us use the binomial expansion. We got this term. Now multiply the terms. I think so. There is no z in the denominator. No need to multiply. Let us look at this expansion. There is no z in the denominator. You got it, right? So there is no principal part of f of z. So it is clear that z equal to a is the removable singularity. So this is the another way, right? Fourth one, tan z by z. So z equal to 0 is a removable singularity. Very simple concepts, right? Now the second type of definition is poles. Once again, I repeat this: poles. Very simple concept. Once again, the point is a isolated singular point, and if we expand the given f of z as a Lorentz series expansion, and it has a finite number of principal part. So previously there is no principal part, so it is called a removable. Finite number of terms in the principal part is called poles. Correct? No terms in the principal part is called removable. Finite number of terms is called the poles. What about infinite number of terms? If it is infinite number of terms, there is a third type of singular point, essential singularity. That is the last type. Now let us see the pole first. Poles, right? See the example. F of z is equal to e to the power z by z. So z equal to 0 is the only singular point. Let us expand e power z 1 plus z by 1 factorial plus z squared by 2 factorial, etc., etc. Let's divide this by z, we get multiplying 1 by z. So we have only one term. So it has a finite number of principal part. The negative powers of z in the denominator. So this is the fine example, the best example for the pole. So here z equal to 0 is a pole, right? Second one, z equal to 0 as well as z equal to 1. Z equal to 0 and z equal to 1. Let us abbreviate this with the help of binomial expansion. Let us abbreviate this with the help of binomial expansion. Then we get 1 by z plus 2 plus 3z, etc., etc. So once again, only one term. I don't say only one term, it may be finite number of terms. So in this example number 2, it has only one term. So that is also the pole, right? At the point z is equal to 0, right? What about the name? I told you that if it is have something like a power, it is called the order. So what is the order of the pole? The order of the pole is nothing but when I use the limit z tends to the point a, z minus a full power n into f of z, the limit not equal to 0, then the point z equal to a is called a pole of f of z and the order is n, right? And the order will be the n. If the given f of z is phi 1 of z by phi 2 of z, then the poles are the solutions of the denominator function. This is nothing but we have already done in the Cauchy integral formula. Once again, the denominator roots are the singular points. Yeah, this is a kind of isolated singular point with the finite number of principal part in the Lorentz series expansion. So that's why this is known as the pole, and the repetition is known as the order n, right? Clear? Let us see the example number 1. F of z is equal to z squared minus 2z plus 3 by z minus 2. So z equal to 2 is the only singular point. Now find out the limit z tends to 2 z minus 2. So here a equal to 2 into the f of z. So substitute f of z, cancel the term first before applying the limit. After cancellation of z minus 2, then substitute z equal to 2. Here we get 2 squared 4, 4 minus 4 get cancelled, so 3 is not equal to 0. So limit value exists at the point z equal to 2. So this is a pole z equal to 2 of order 1. Why it is order 1? Because power is only 1. Order 1 means is often called as simple pole. Order 1 means simple pole. Order 2 means double pole. Clear? Once again repeat this. If you want to find the order of the pole, the corresponding term get cancelled. That is the idea. We don't want to retain that term, because when we retain the term, obviously this becomes 0, isn't it? Because how we will get the pole? The denominator equal to 0. So obviously the denominator equal to 0, anything by 0 becomes infinity. So first our aim is to eliminate the corresponding terms, then apply the limit. The limit exists, then this point is called a pole. The order is 1 here, it is called simple pole. Let us see the example number 2. Yeah, it's very interesting. If f of z equal to 1 by z minus 5 whole power 3 into z minus 4 whole power 2, here z equal to 5 is a pole of order 3 power, right? As well as z equal to 4 is a pole of order 2, is often called as double pole. Now let us find out whether the limit is exist or not. Let us check it out. Limit z tends to 5, so z minus 5, what is the n here? 5, 3, n equal to 3 here, so put n equal to 3 here, multiply the given f of z. So what I told you, that if you want to find the limit of the pole z equal to 5 means that term get cancelled. After cancellation of z minus 5 whole power 3, the remaining is z minus 4 whole squared. Substitute z equal to 5, 5 minus 4 is 1, 1 square is 1, 1 by 1 is 1, not equal to 0. In similar manner, put z equal to 4. So limit z tends to 4, z minus 4 whole square f of z. After cancellation of z minus 4, we have here 1 by z minus 5 whole power 3. So that means that putting z equal to 4, 4 minus 5 is minus 1 whole power 3, it is, I think so, minus 1. And here it is not equal to 0, isn't it? So limit exists, as well as then the points are called pole with the orders. Order 1 means simple pole, order 2 means double pole, right? These are some problems for you. Just we have just see that few examples. The first one is a pole 3 of order 3, correct? Fourth one, what is a pole? 1 order 2, double pole, right? Minus 2 order 1, a simple pole. Plus 4 order 1, simple pole. What about z square plus pi squared? Is equal to plus or minus I into pi. This is either z equal to 0 or cos z equal to 0. That means z equal to 0, z equal to plus or minus pi by 2, plus or minus 3 pi by 2, etc. etc. Eighth one, minus that is z square plus 1. If it is z square plus 1 means z equal to plus or minus I whole power 2. So plus I of order 2 minus I of order 2. What about this one? Z square plus 16. That means that z square equal to minus 16. So z equal to plus or minus 4i. What is order? 3. What is order? 3. Plus 4i minus 4i, order 3. Plus I minus I, order 2. Double poles, right? So this is the 8th example. 9th example, tan z. Yeah, the sin z by cos z. So cos z equal to 0 when we get plus or minus pi by 2, 3 pi by 2, etc. etc. So these are the some interesting examples on under the poles category. Now find some order. What is the order of the pole z equal to 0 for the following? Z equal to 0 of order 1, z equal to 0 of order 2, double pole, z equal to 0 of order 5. Got it? That's it. Very good, very good. Well done. Keep it up. Show that the singular points of each of the following functions are poles. Determine the order as well. So I think when take z equal to common, z minus 2. So z equal to 0 and z equal to 2. So simple poles of order 1. Z equal to 0 of order 4. plus or minus of order 1. Here does simplify this, will get plus or minus of order double pole. Check your answers. This is the exercise questions. Just given the answers. And fifth one, sixth one, seventh one, 1 of order 2, 0 of order 2, 3 of order 2, double poles. 1 minus cos z equal to 0, so cos z equal to 1. When we get cos z equal to 1, 0, right? Or maybe 2 pi, 4 pi, etc., etc., right? Yeah, this is z equal to minus 2i. Simple. Got it? The third type of the singular point. Third type of the singular point. So what's the first type? Removable. When we say that it is removable, there is no principal part. Second type is pole. It has finite number of principal part. Finite number of terms in the principal part of the Lorentz series expansion of f of z. At that point z equal to a. Now the third one, suppose when we expand the given f of z as a Lorentz series expansion, at the point z equal to a, here z equal to a is entirely an isolated singular point, because isolated singular point only categorized into 3 types: removable, no principal part, poles, finite number of terms in the principal part. Now finally, essential singular point, it means that infinite number of terms in the principal part. Got it? Right? So this is the third type. Let us see some example. Yeah, f of z is equal to e power 1 by z. Obviously z equal to 0, because when putting z equal to 0 we get e power infinity is infinity, so it fails the nullity at the point z equal to 0. This is a one point, so it is isolated. If I expand this with the help of exponential function, we get there are infinite number of z terms in the denominator, z square, z cube. So that's why this is the example for essential singularity, right? Second one, z square into sine 1 by z is equal to 0. So expand here once again with respect to the sine theta, sine z in powers of z, then multiplying z square into that term. Once again we found that z in the numerator, z cube in the numerator, z power 5, etc., etc. So it has an infinite number of terms in the principal part, so it is known as the essential singularity. Got it? The same way, the third example, 1 by z minus 1. So z in the denominator, it is the essential singularity when z equal to 1, right? Because when you put z equal to 1, 1 by 0 becomes infinity. So that's why this is the example for the essential singularity. Now this is the another topic is called residue at a pole. So till the previous we have discussed what is meant by singular point. A function is not analytic at a point z equal to a is called a singular point. Suppose there is one and only singular point, it is called isolated. Isolated singular points can be classified into 3 types: essential, removable, and poles. Otherwise, in the order way, I simply order it. Removable means it has no principal part in the Lorentz series expansion. Poles, it has a finite number of terms in the principal part of f of z when we expand as a Lorentz series expansion. And third one, the final one, is essential. It has an infinite number of terms in the principal part. Okay, got it?